Hi guys, my name's Gio. I am a search engineer at Etsy, and I'm here to talk to you about some of the cool stuff that we do with Solr. So before I begin, I'd like to apologize for quite about a dozen things. To start off with, there's a couple things that were in the abstract that I'm not going to talk about. Those are A/B testing, internationalization, and continuous deployment. I was a little ambitious with the abstract, and I really couldn't fit it into a half-hour talk, but feel free to bring up any of these topics during the question and answer at the end. Send me an email or come chat. The other thing is my slides are pretty dark and these projectors are pretty dim, so it's going to be tough to see some stuff. There's not a whole lot we can do about it, but you guys are going to get a copy of the slides, and I hope I can make up for it with some enthusiasm. So with that being said, let me tell you a little bit about Etsy. Etsy is the world's marketplace for handmade and vintage goods. You can find all sorts of stuff like clothing, artwork, houseware. All the boots that I'm wearing right now I actually purchased on Etsy. Incidentally, working at an e-commerce site is sort of difficult if you like shopping because you're supposed to shop at work. But really at its core, Etsy, what we're trying to do is we're trying to create a new economy. We're trying to create an economy that's less about these giant conglomerates and people just anonymously, purchasing, and more about, people purchasing locally, about people purchasing from small businesses, about people, exchanging goods with other people, and incidentally, being able to understand the stories behind the items that they're purchasing, being able to speak to the people that are at the other end of the exchange. We really want to bring back some of the human elements that I think the 21st century has sort of erased from commerce. And so in that respect, it's kind of a touching place to work. It makes you feel good every day you walk in. It seems like, hey, in our own special way, we're doing something a little different that might, help the world. There's 10 million active listings right now on Etsy, and that number is growing significantly. On an average day, we get about 500 queries per second, and this is like an average day, say in September. It's really not by any means high traffic. So in the holidays, we'll probably double that number of queries per second. And so the architecture we're going to talk about right now definitely gets a heavy amount of use and handles it pretty well. So with that, let's talk a little bit about what search at Etsy looks like. So at the head of our infrastructure, you're going to see a set of web servers that have a very typical LAMP stack. They're running a CentOS distribution of Linux. They're running PHP inside of Apache and talking to a MySQL and Memcache backend. Now, when a search request enters one of our web servers, we send that request via thrift to our search cluster. The search cluster is made up of a single master with many slaves. One of those slaves is going to pick up that search request and reply back with only the primary keys of the listings that are relevant to that search. Then the web server is going to take those primary keys and look them up one at a time in our sharded MySQL database. And naturally, there's going to be a lot of that's already going to be in Memcache. And from that data store, it's going to retrieve all the other information it needs to render that page of search results. So let's talk about what Thrift is. Thrift is a library that allows you to really easily create cross-language services. So if you need to communicate to a service that is written in a completely different language, Thrift and a lot of other sort of RPC serialization libraries are kind of what you want to use. Now, the way to use it is actually pretty straightforward. You'd create a Thrift interface like the one you see in front of you. It's really simple and it's sort of hard to see, but the idea is that you're declaring a service called search, and it only has one method called search, which is in brown. It takes a query and it gives you back a listing results object. That object is a struct made up of a 64-bit count and a list of 64-bit integers that represent those primary keys. Obviously, our interface is a lot more complicated, but this is just kind of a pared down version of what an interface could look like. And in fact, this interface compiles and you can use it to generate code. Now, in our case, since our search stack is written in Java and our web stack is written in PHP, what we want Thrift to do is to essentially generate server-side code for this service that's in Java and generate client-side code that's in PHP. And here's some examples of what that might look like. So the Java side is an interface that essentially completely mirrors the Thrift interface that we just saw. And the idea is that you are then essentially have the responsibility to take some class and implement this interface, and then you can instantiate a Thrift server, and the Thrift server will just start serving it. Now on the client side, you can almost use it right out of the box. So we have a search client class that has a search method. As soon as you choose a protocol and transport, you can essentially just call that method and point it at a server, and as long as someone's listening on the other end, you should get a response. Now, why do we use Thrift? There's two key reasons. First is service encapsulation, and what I mean by that is there's very clear RPC contracts, right? Both sides of the service understand what the inputs and the outputs are, and especially when compared to the sort of like really fast and loose world of creating, of accessing your data through Solr's HTTP interface. And in addition, one really nice benefit is that if you choose to use one of Thrift's binary protocols, you're probably going to enjoy reduced network traffic as opposed to using a more verbose protocol like JSON or XML. And incidentally, Thrift is one of many other sort of RPC libraries out there. At the time we picked Thrift because our friends at Facebook were having good experiences with Thrift, and they were using it for a lot of stuff, and it came well recommended. It turned out to be really easy to use, so we kept using it. Maybe we'll use something else in the future, like Avro or one of the many other options that there are. But for right now, Thrift is really serving us well, and we're really happy with it. Now, probably the more interesting question is why only return IDs? And this is something that in many ways sort of stands out from other places that use Solr. And the first reason is really obvious. If you only return IDs, you don't have to store anything else in your index. And that means your index is going to be a lot smaller because stored fields generally grow linearly with respect to the number of documents in your index. And if you think about the nature of how stored fields work, that sort of makes sense because they're an uninverted index, right? You're storing essentially one piece of information per document per term that you're storing, versus the inverted index, which is obviously a lot more compressed. But in addition to that, what really drove us to do this, aside from the obvious savings of smaller index, you have less I/O, more of your indexes in memory, is the fact that we don't need Solr to do this, because looking up all these details in our infrastructure is really easy to do, right? We're really good at scaling primary key lookups because we use a sharded MySQL scheme that was sort of pioneered by Flickr, and really a lot of the engineers from Flickr came over to Etsy and sort of brought that over to us. And the reason I think this is sort of startling is that a lot of people, when they first start using Solr, they get a big performance boost out of using it, right? Because they store a ton of fields in Solr, and then they use Solr to serve the entire page, and they're like, hey, Solr is so much faster than going to the database. Let's just use Solr for everything. But really, Solr's core competency is that it's a search engine, right? If at the end of the day, the primary data store behind your website is not good at retrieving the details of some object that's sort of core to your business model, you probably have a problem that you need to solve, right? Because somewhere along the line, you're going to need to retrieve those details from that data store. Unless, of course, Lucene and Solr is your primary data store, which is sort of a wacky idea, but I guess some people are crazy enough to do it. I'm not going to go into too many details about our MySQL setup, but you can read about it if you just search for MySQL in Flickr or Etsy, or just send me an email when we can talk about it. It's sort of tangential to this, but I think it's an important point that people should take into consideration. So let's talk about the search server. Each one of our servers is identical in terms of the code and hardware that they have. And the only difference between any of the nodes in our cluster is environment variables that tell that node whether it's the master node or whether it's a slave. What's really convenient about that is that it keeps our stack really, really simple. It's really easy to support. And in addition, if we found ourselves in a situation where our master node went down, we can easily take one of these slaves and replace master with one of those slave nodes. In fact, that's one of the things that we do every year leading up to the holiday season. We like to do these game day exercises where we literally pull the plug on our master node and see how quickly we can spin up a new one. And it really turns out to be a pretty simple process. Now, on these search servers, you'll find a single Java process that has Solr running as a Jetty servlet. I think this is a sort of a really typical setup. And the reason we do that is because you get to use the HTTP interface, the admin UI. That's really convenient. You can use replication over HTTP, right? All the good stuff that we're used to using from Solr, we use through Jetty. But in addition, we also have a set of Thrift servers, like I talked about earlier, that are the ones that are actually servicing the search requests. Now, aside from that, we have a bunch of sort of special one-off request handlers that do interesting things. Probably the most relevant at this point in the discussion is our smoker. And the smoker is kind of like the admin request handler. It's a health check, and what it does is if you hit this URL, it'll perform a simple search across all the thrift servers that we have inside this Java process, and return an OK, a 200 if everything's fine, and obviously it'll return an exception otherwise. And we have alerts set up that monitor the smoker and will page an engineer if ever one of these servers weren't to respond. Now, on each of these nodes, there's a set of crons that fire. And these crons fire at their scheduled intervals, and they'll basically check, hey, am I the master according to the environment variables? And if they are the master, they'll go on and do some work, but otherwise they'll just stop. Now, on master, there's two kind of core processes that keep our site and search up to date, and those are the incremental indexer and the external file field updaters. So the incremental indexer is a process that essentially checks a file stamp on the local file system to understand how recently updated the data in our index is, and goes to whatever data store that index is fed from and fetches all the data that that has essentially been updated since then and adds it to the index. And the graph that you see right now, this is a ganglia graph of our index age in seconds. So you can see that it's growing to the point where it gets to about 400 seconds. The incremental index runs, and we come down to about 60 seconds of staleness. In addition, we also have a kind of a similar process for external file fields. If you've never used external file fields, I highly recommend you go check out the wiki documentation for them. They're a really convenient way to incorporate pieces of information into your index without actually having to re-index. So these external file field updaters have a very similar process where we go out and get a bunch of data about the listings or other items in our index, create external files, and distribute them to all our slaves. Now they have a pretty clear idea of what the search cluster looks like. It's a single master, many slaves, servicing requests over thrift. Let's talk about load balancing. So not so long ago, we started off doing something really simple, using a library that came with the PHP thrift code. It's called tsocket pool, and what tsocket pool does is it just randomizes requests from your PHP client amidst all the nodes in your cluster. And it also takes care of retries. So if a search request came in, the web server tried to connect to host 2, and host 2 was down and was unable to create a TCP connection, tsocket pool would automatically retry another host, and it would also mark host 2 as down inside of APC. So APC is an in-memory cache that's available to any request to the same Apache web server. So any web requests that subsequently hit that same web server are going to see that host 2 is down and are not even going to attempt to connect to host 2 as long as that cache entry survives. And that cache entry right now, we mark a node down for about a minute. And this works pretty well. It served us pretty well for quite some time. But just blindly randomizing a request has a bit of a downside, and that's that if you issue the same query multiple times, you're probably going to end up servicing that same query from many different nodes, right? So jewelry, if we search for it a bunch of times, we'll probably search for jewelry on different machines every single time that we hit that website. What if we could do something like this, and every time someone searched for jewelry, we hit the same node? The effect would be that you would probably get a cache hit, right, after the first every jewelry query, and every subsequent jewelry query would probably hit the cache. And we like to call server affinity. It's really, really nice. It significantly increases your cache hits, and it has a really nice scaling property as well. So as you add nodes, you're essentially sharding your queries even more amidst all those caches. So adding slaves not only gives you additional capacity, but also increases your cache hit ratios and potentially decreases latency, which is really, really convenient. So let's talk about how that works, because there's some subtleties to it. And this is literally the gist of the algorithm. It's really hard to see. I'm super sorry about that. By the way, I feel like this is a grievous faux pas. Putting PHP up on a slide at a Lucene conference just feels dirty, but what can I do? But I'll give you a quick summary of it. So the idea is that you start off with a list of hosts, let's say 1, 2, 3, 4, that you're going to try, right? So you try to connect to host 1. If that fails, you try to connect to host 2, and so on and so forth. So what we're going to do is we're going to reorder that list and affinitize it to a particular query. And the way that we do that is we iterate over that initial list, and every iteration we pick one host from the first list and we put it on the new list. And the way that we do that is by taking an MD5 of the concatenation of the number of servers in the query, then modding that by the number of servers that are left to pick. Now, why are we rehashing this key every single time that we iterate? And really that's the crux of the entire algorithm, is the fact that we're doing that. To understand that, let's take a more naive approach. Let's say for a second that at the beginning of this algorithm, we just hash the query. And we said, all right, we're going to hash the query, we're going to iterate over the host. Every iteration we'll take the mod, pick a host, and we'll get ourselves a list of hosts that we're going to try. The net effect is that for two different queries that hash to the same value, you're going to end up with the same list of hosts. So far so good, right? That's kind of what we wanted. We wanted to affinitize this to a certain set of servers. Well, not exactly, because what happens if host 2 goes down? If host 2 goes down, all of the traffic that was on host 2 is going to go to host 3. You're going to effectively double that traffic, probably bring the host down, right? This is not what you want your load balancer to do. Really, if one machine goes down, you want to distribute those requests amidst all the nodes in your cluster. And that's why rehashing every single iteration is the key. Because on one iteration, say the first one, you may pick the same key, and you may end up picking the same host, but it's really, really unlikely that you're going to end up picking the same host every iteration, and thus, in this example, we may have picked host 2 in the first step, but on the subsequent steps we pick different hosts, and thus, depending on how evenly distributed your hashing function is, you should presumably do a fairly decent job of distributing those queries evenly across the rest of your nodes. Now, what did this do for us? It took our query cache hit ratios from about 2% to 20%, which is huge, right? Because a lot of people, they even turn off the query cache because they have query distributions that are really long-tailed. They really don't get a lot out of it, so it's not even worth the memory that it's consuming and the GC overhead that it incurs. But using this really simple technique, we were able to significantly increase that. And again, as we grow our cluster and as we grow as a website, it's only going to get better. Now there's some caveats. Like before you go home and try this at your company, you should be aware of that. First of all, you're obviously going to get much better query cache hit ratios if you were to stem the query before you actually hashed it. But doing the full analysis chain could be tricky, right? Not only, especially depending on what your web server architecture is, but it also could be a little heavy-handed, right? It could be a lot of extra work just for picking a server. You probably don't want to do it. Right now, we do something really fast and loose, and we have some simple regexes that sort of do kind of ghetto stemming on the client side, and it serves us all right. It also gives you a good instinct for what our engineering culture is like, right? Like, do something simple, get it out there, let's see how it works. If we need to get more complicated, we'll get more complicated. But this works fairly well for us right now. The other thing to be careful about is the query distribution. So it's entirely possible that your application has queries that are much more popular than other queries. In Etsy's case, for example, it's very popular to search for the blank query, to search for nothing and just browse. And so what we did is we looked at a query distribution for a couple months, and we said, okay, overall there's no queries that are really, really hot except for the blank query. We're literally going to make a blanket exception for this query, and we're going to say that blank queries they're not going to be affinitized. They're just going to continue to be randomly distributed. But you really need to look at that query distribution because it's going to vary between applications, and it may be the case that you need to do something more complicated. So let's switch gears a little bit and talk about replication. So this is a story actually that was pretty difficult. It was a bit of a process, but it's something I'm really proud of, and at Etsy we're really proud of, and hopefully you guys will get to enjoy the fruits of our labor as well. So let me tee up what the problem was. So this is a graph of the index age of our slave nodes. So each color represents one node, and you can see, similar to the earlier graph, right? The indexes on the slaves get older and older and older. The incremental index runs, the index gets replicated, we go back down to close to 0 age. But then at 7 o'clock, something really dark happens, right? For about an hour and 20 minutes, our index is getting older and older. And the reason for that is that at 7 UTC, we like to optimize our indexes, right? Because, hey, we want to keep things nice and fast. But a consequence of the optimize is that you've essentially created a brand new segment that's the size of your entire index, and you need to transfer that to all your slaves. And it turns out that, with HTTP replication and 11 slaves, this 9 gig index took about an hour and 20 minutes to transfer. And this is an hour and 20 minutes that there's literally no updates to our site. And since, as I was mentioning to some folks I was discussing with this earlier, these people live off our website, right? In many respects, we're responsible for their livelihood. So an hour and 20 minutes without updates is an hour and 20 minutes that they could potentially be losing out on sales. And naturally, they were pretty, not psyched about it. So we decided to do some investigation. This is a graph of the I/O, the network I/O, on a single slave during this transfer. You can see that, for the first parts of it, we're going at about 2 megs per second, shoot up to 8 megs per second, but this is really sort of kind of pathetic, right? Like, we're coming nowhere close to fully utilizing the bandwidth that we could possibly have. And so we went and did some research. We started experimenting with compression, we experimented with chunk sizes, but no matter what we did, we really couldn't significantly improve this outlook. And that caused us to step back and think and say, think about it. Even if we improve this, right, and we continue to use HTTP replication, the fact stands that this really has poor scaling properties, right? Because even if you were to fully utilize the bandwidth that one slave had, at the end of the day, you're going to have one separate transfer for every single slave in your cluster. And at some point, you're going to get bottlenecked by the NIC on your master node. And there's really nothing you can do about that. So we said we really want to look into another way to potentially do this. And so we started experimenting with rsync, which I think Mark had really successful experiments with. And we as well had some successful proof of concepts with it. We found a simple C implementation, just a shell script, and started playing around with it. So in our development environment, we shipped around some indexes. Sorry, let me step back and explain what this is. So what I mean by multicast rsync is using UDKey multicast to essentially broadcast all the bytes of the files in your index, and each slave subscribes to that broadcast. So you are effectively only transferring the data once from master, but tons of people are listening to that transmission. So anyways, we tried it a bunch of times, worked really well, tried it in development, tried it with some small files in production, seemed to work really well. Then the day came where we were like, let's try this proof of concept with a full index in production to a couple nodes. So this is the IRC conversation of the engineer in question letting one of our ops engineers know that he's about to try it. And you can see that, about 6 minutes later, the site was effectively down. It wasn't a very good day. So it turns out that multicast is really effective, but the way it works is it's broadcasting, right? So every node in your network is going to receive a packet for that transfer. So in a large network, that means you're going to be routing a lot of packets. And if you're on a network that shares infrastructure in between your search nodes and say your database servers and your web servers, you can cause a lot of damage. And that's effectively what happened. So at this point, our ops guys were like, man, all right, let's do something else. They're like, let's try BitTorrent. And we're a bit skeptical about BitTorrent because we've heard talks of people like Twitter using BitTorrent to deploy code to hundreds of servers at a time, but really our search cluster isn't that large, right? So we didn't think we could possibly get that much throughput from BitTorrent. But our ops guys were pretty excited about it, and we said, all right, let's do a proof of concept. And literally over 2 days, they found a Python script called BitTornado, started tweaking it, and you can see here towards the end of it, they're pushing 140,000 packets per second. The transfer took a couple minutes. They did a really, really great job. I mean, I don't know about the ops guys at your company, but the ones at our company they're like meth addicts cleaning a kitchen, right? They're just like tweaking scripts all day. And we were really excited about it. They gave us a script and they said, hey, here's a BitTorrent script, you can use it, it works really well. And we sat back and we said, well, incorporating this script into the whole, replication process, it seems a little, it seems a little cumbersome, it's going to be annoying, and other people probably suffer from this problem, right? There's got to be plenty of other people that have large indexes that you want to replicate to a large number of slaves. So we thought, let's incorporate this into Solr so we can commit it back to the community and other people can benefit for it. So we first had to find ourselves an implementation of the torrent protocol in Java, and we found one in ttorrent, but it was not exactly what we needed. It was missing a couple things, so we forked it, and you can see it there on GitHub. The main things we added were multi-file support for stuff for files greater than 2 gigs, and also some performance enhancements like multi-threaded hashing of the pieces inside the BitTorrent. So using this, we've essentially created 2 new handlers that you can add to your Solr configs. They are a torrent tracker handler and a torrent client handler. And the way it works is pretty simple. Whenever a commit or the server starts up, master generates a torrent file, and at this point, the slaves will essentially check to see just like HTTP replication, the index version of master is later. Master has a new torrent file, we'll grab that torrent file. Master also acts as the tracker of the torrent and as the initial seeder of that torrent. So at this point, the slaves start up their torrent clients and start hitting the tracker through the announce URL and essentially transferring that index. So at the very start of the transfer, master's the only one that has any of the data, but as soon as you pull over a couple pieces, all the slaves start talking to each other. And it worked pretty well. So this is the I/O graph of one of our slaves using the new BitTorrent code, and you can see that really tall skinny spike was the entire index transfer. You can see that it was pushing almost 40 megs per second. The green is inbound traffic and blue is out. As you would expect, we're pushing out almost as much traffic as we're pulling in. The other green graphs, by the way, are normal HTTP replication of other cores that we're getting optimized soon thereafter. And this is the graph for the entire cluster during that transfer, and it's about, I think, 350 megs per second. I can't see it that well from right here, but this is really exciting. We're not quite ready to hand it over to the community right now, but we're going to do it before the end of the year. We literally rolled this out to our production cluster 2 weeks ago. So it's been working really, really well, and hopefully sometime soon you guys are going to be able to enjoy the fruits of BitTorrent as well. So I've been, again, I actually have probably like 10 or 15 more slides, but still kind of running short. I'm going to breeze through maybe one more section and then open up for questions. And this section, I want to talk about interoping with Solr, and I think people are hesitant to write code for Solr, but it's really easy to do, and that's one of the benefits of using open source code from Solr. And when I want to start off with query parsers, and the reason I want to do that, it's a really funny story actually. When I was writing the abstract for this talk, I was asking some of the guys on the team, like, hey dudes, what's some cool stuff that we do that other people should do? And my colleague Andrew has said, people should write more query parsers. And I was like, query parsers? That's so boring, right? Like, that's really not interesting at all. And he responded, well, writing query strings is for suckers, man. And honestly, I can't agree more. By the way, this is a picture of Andrew on the sidewalk in downtown Brooklyn fixing the search stack while smoking a cigarette during a fire alarm. Pretty remarkable guy. Anyway, so I decided to go through a little exercise to try and help people write query parsers because they're pretty cool. And to give you the impetus to do so, the use case that we're going to walk through is person search or people search. You can search for people on Etsy, and we're going to do a really kind of pared down, sort of simple query parser. And there's much more complexity than you can add to it. But to understand what we can gain, let's first look at what that query string would look like for a really simple Q parser that we're going to write. And this is actually only one if branch of the Q parser that we're going to write, and it's actually wrong. But after about half an hour, I got so sick of doing this that I decided, like, this is as close as it gets, and it's horrendous, and I can't believe people still do this. So this is what the logic would look like for that. And this is what it looks like after you've written a custom Q parser. So what are the steps? First, we're going to write a new person real name Q parser. It extends Q parser. Essentially, you instantiate what is a nebulous cloud of code and move on to another nebulous cloud of code. So the gist of the Q parser is that you have to have a parse function. At the top of this parse function, we're creating a term query for a person's full name. So if you search for Giovanni Fernandez-Kincade, if we get an exact match on full name, we're going to give this guy a crazy boost. We want that to be the first result. Simple. Then we're going to do something sort of silly. We're going to tokenize this query, and we're going to say if there's two tokens, right, we're going to assume that those two tokens are the first and last name, because that's like not a horrible assumption to make in the United States anyways. And what we're going to do is create another query that is an AND of the first token searching for that in the first name field and the second token in the last name field. Then otherwise we'll do a big OR amidst all those fields, and we'll just add those two together. So even though you can barely read it, it feels like a pretty straightforward set of code, right? And compared to this, it's much easier to follow. So I highly encourage you guys to go out and write Q parsers. To finish up what you need to do, you need to expose this Q parser by writing a Q parser plugin. And really the only thing interesting there is the create parser will return the new Q parser that you created. And finally, you can plug that curate parser into your Solr config, another nebulous cloud of XML. All right, so with that, I think we have about 10 minutes for questions. So yeah, if you guys want to ask questions, I don't know if we have a microphone, but I'll try to repeat the questions. What's up?
How often do you build index from scratch?
So we optimize every day. So in terms of replication, that's effectively rebuilding the index every day. How often do we reindex our data?
No, actually, I was asking it. The second question was when you send the index using the BitTorrent all the slaves.
Yep.
Have you ever experienced like performance problems with CPU?
We haven't, because we're very careful to. So the reason that BitTorrent clients may end up using a lot of CPU is that what BitTorrent does in order to understand what pieces it needs or what it needs to download is it takes all the files, it breaks them up into pieces, right, and it hashes all of those pieces, right. So the torrent file has a list of all those hashes, and so each one of the slaves will take that list of hashes, compute a list of hashes for the files that it has locally, and then compare and say, okay, I need these pieces over here. So that hashing, depending on how you implement it, could be CPU intensive, and if you multi-thread it, obviously it could impact your server. So we do multi-thread it, but we're very careful to only use 1 or 2 cores on our slaves, and naturally that's something that you're going to have to account for, right? If your slaves only have a single core, yeah, that may not be the best idea. But in our case, our slaves have 16 cores, so leaving a core or 2 to do hashing is not so bad. And actually on the master node, when it's doing hashing, we use far more parallelism.
Just the point. What
Yeah.
you said before that when you were trying multicast that you made your side down.
Yep.
I even made the phone of the office down.
Right. It's dangerous. And actually, you can another way around this. We could have used multicast and continue to use multicast by setting up a separate network infrastructure for replication. And in fact, we did that. So we have BitTorrent and we have a separate network infrastructure. The reason we didn't use multicast is that our network engineers were like, listen, if it just so happens that someone crosses the wires, we might be in a really bad place. So better safe than sorry, and BitTorrent works really well. That being said, BitTorrent is not without its dangers, right? You are not going to have a routing problem, but you could very easily consume the bandwidth in your network. So you need to bear that in mind.
Any aspiration of writing this BitTorrent thingy as a native Java plugin? Oh,
it's written as native Java. So the tracker in the client that the GitHub link was there for, that's up there right now, and it's a native client that fully works. By the way, there's not a lot of good native Java clients for this, which is why we had to fork that one. So if you need that one, go ahead and use it.
I understood it was a Python.
No. The proof of concept that our operations team did was in Python. But then we decided that just going out to the shell like in the middle of the replication workflow just sucked. So yeah. All right. There's no more questions. Thanks a lot for coming.